So let's see what we can do today. And then we can make progress. So we have the last astrophysical phenomena that I want us to look at during this course, which is gravitational deflection of light. Okay, gravitational deflection of light. From your basic knowledge of optics, you know that light, if it can either be transmitted by a medium, can either be reflected, it can either be deflected, or it can be absorbed. Is that not? Those are the four things that happen when light is approaching be a medium. Okay, so we are going to see that gravitation has a tendency of deflecting light. Okay, you must have seen also that a prism, when light passes through a prism, a glass prism, okay, there is some sort of, maybe it's moving from air to glass. There is some change in direction, which is what we are calling a diffraction. Okay? It's a diffraction when it moves, when it changes direction. But in this case, we are looking at a slight change in path. We know that light travels in straight lines. Okay? But we will see that when light is approaching a gravitating material, there's a slight change in path. And that's what we're calling a deflection. It will not continue in that path. The gravitational field, the intense gravitational field will cause a change. There will be some sort of deflection. Okay? So that's what we want to appreciate. Okay, and again, we'll work within the context of Schwarzschild's metric. And then the other day, we agreed that light moves along what we call a null geodesic. Light moves along a null geodesic. Okay? Moves along a null geodesic. So if that is true, then the left-hand side of Schwarzschild's metric will also be 0. We agree that this is the left-hand side. Okay? So we have our c squared into 1 minus 2 gm over c squared r dt squared minus 1 minus 2 gm over c squared r to the power minus 1 dr squared minus r squared d theta squared minus r squared sine squared theta d phi squared. Okay, so that will be true. And then again, we are going to restrict ourselves to the equatorial plane to make life easier for us. Okay? To make life easier for us, we are going to restrict ourselves at the equatorial plane. And building on what we said yesterday, this is going to go. And this will be 1. Because at the equatorial plane, theta is pi over 2. Okay? So we'll end up with this is no longer there, and this is no longer there. We'll end up with that. Okay? Then again, if we divide all through by the proper time, we divide all through by the proper time, this will become what? This will become, and this will become, okay? We divide all through by that. But yesterday, we agreed that T dot is of the form A into 1 minus 2gm over c squared r to the power minus 1. And we agreed that phi dot is the same as yesterday we used L. You can decide to use B. Okay, it doesn't change anything over r squared. Okay, at the equatorial plane. So we'll now substitute this into this. We'll substitute this into this. So if we do that, okay. If we do that, what do we get? So, remember, this is squared. So there will be a minus 2 here. So if I put it here, this one will end up with a minus 1. Are we together? So I will have a minus 1 here. And then I will have an a squared somewhere. Are we together? And then for the phi dot, I will have this over r squared. So remember this will be squared, since this is squared. And this will be to the power 4. So I'll end up with minus b squared over r to the power that. Is that not? I'll end up with that. Thank you. So this goes. Are we together? So we have that. The next thing is for us to write our r dot. What is left is just r dot. Remember the same thing we did for the planetary equation yesterday. We tried to substitute all the others and we're left with r dot. Then at the end of the day we came out with a differential equation which we called a planetary equation of motion. So it's almost the same thing we are going to do here. But we are now going to get a differential equation that will describe the motion of a photon. Okay, it's no longer going to describe the motion of planets, but it's going to describe the motion of photons or light. Okay. So, yes. There was an r squared somewhere here that reduced this to 2. Okay, so that r dot, but that r squared was able to Yes, we have added an a here. Okay, a is just a parameter. It's a constant. Okay, if you remember, we had that a, but we brought some arguments that if t is turning to 2, okay, if t is turning to 2, r tends to infinity, and a will be equal to 1. Okay, we were able to break that argument yesterday. Okay, so it's just a constant parameter we are introducing there to make our problem more general. Okay, that is why we are introducing the e. So we have that. So again, we'll try to write r as a function of phi. Okay, we'll write r. R dot is partial r by that. Is that not? Or r dot is that, which is the same as partial r by, let me use phi. Partial phi by that. Okay, and this will be okay, that will be that, and then this will be the same as b over r squared dr by d phi. Are we okay with that? Okay, it will be that. So from there, okay, so we can substitute this into this equation. Okay. So substituting that into that equation, we are going to have 0 equal to a squared c squared into 1 minus, what did we do here? It's okay, minus 2gm over c squared r to the power minus 1 minus 1 minus 2gm over c squared r to the power minus 1. So in place of my r dot squared, I will put b over r squared gr by d phi, all of that squared, minus b squared over r squared. Okay. What if I multiply all through by this? If I multiply all through by that. Okay. If I multiply all through by that, this will go, and only this will have that. Is that not? So I'll end up with 0 a squared c squared minus b squared r to the power 4, that squared, okay, minus b squared over r squared into 1 minus 2gm over c squared r. So I have that. Okay. I'm interested in this, so I can take it to the... I'm interested in this, so I'll take it to the other side of the equation. So if I do that, I'll have just b squared over r to the power 4 gr d phi, all of that squared, equal to a squared c squared minus b squared over r squared into 1 minus 2gm over c squared r. So I'm going to have that. Okay. Which one? Why is it not having? We are multiplying by this. So 1 and minus 1 will, so this and this will go. We are multiplying by this. That's why you only have this one having it. So this one will reduce to 1. This other one will also reduce to 1. Are we together now? Okay. So we have that. Okay. So again, we cannot work with R. We need U. We need U. With R, it will be more. It will not be easy for us to appreciate what is happening. So we need U. So again, we introduce a U, which is 1 over R. Same thing we did yesterday. Okay? Same thing we did yesterday. This is a very powerful technique. Okay, that is, it looks so simple, but it's used most of the time to convert our differential equations to a form that we can easily appreciate. So again, our dr by, what we have here is dr by d phi. Our dr by d phi will be our dr by du, then our du by d phi. Okay, which will be minus u to the power minus 2 du by d phi. Okay, so we can substitute that into our equation. We can substitute that into our equation. But before doing the substitution, we can decide to remove this from here. Okay, so that this will remain on its own. So we'd have to divide all through by b squared and multiply all through by r dot. So if we do that, we are going to have a b squared here. We are going to have r to the power 4 here. We are going to have this b squared is going to drop. Is that not? And then we now have r squared here. Okay, so this will now leave from here. So we'll have something like that. Okay, so we can now substitute our, so we are substituting that. So we're substituting that. So our dr dphi will be all of that squared. So this will give us, when you square this, what do you have? You have u to the power minus 4. Okay, then you have du, the phi, all of that squared should be equal to, what is r? R to the power 4 will be 1 over u to the power 4. So it's going to give us a squared c squared over b squared. Then we have u to the power minus 4. Is that not? Okay. Minus, if I expand this, I'm going to have u to the power minus 2. Okay. Minus plus. So there's minus here, there's minus here. So I have plus 2 gm over c squared. So this r will cancel one of the r here. So we're left with an r here, which is u to the power minus 1. Is that not? So how do we eliminate the minus? U. Multiply all through by what? Multiply all through by, how do we do that? U to the power 4. Okay, so if we multiply all through by u to the power 4, we are going to have du, the phi squared equal to a squared c squared or b squared minus u squared plus 2 gm over c squared u cube. So what next? What do you think we should do next? We need a second derivative. So we'll differentiate this with respect to phi. Okay? We differentiate that with respect to phi. So if we do that, we are going to have 2 du d phi d squared u d phi squared should be equal to, this is a constant, so this is 0. Okay, 0 minus 2u du d phi plus 2gm over c squared. This will become 6, go. This will be 6 u squared du by d phi. And again, our du by d phi will disappear. And we can divide all through by 2. Okay? So we do that, we are going to end up with d squared u d phi squared. Okay? Plus plus u go plus u is equal to 3 gm over c squared u squared. So we are going to end up with that. Yes.
What if we just take the derivative from the split out that result? Yes, instead of going to that place.
No, it will not. It will not. But the only thing now is that when you get here, you have to do this twice. It's the same thing. Okay? So you have to do this twice to get what to substitute there. So you can decide to follow that path. It will give you the same thing. Do you get the point? So you can decide to differentiate from here. And then before you now do your substitution. So in your substitution, you not only end with dr d phi, but you have to go to d squared r d phi squared. So you need to find d squared r d phi squared, which is d phi of minus u squared du d phi. Then you go through the same procedure. Okay? You go through the same procedure. So it's the same. It's the same. So actually this is the equation we are looking for. This is the equation we are looking for. Okay? It's just the differential equation that is describing the gravitational deflection of light, or the motion of light in the presence of a gravitational field. Okay? So again, the solution of that equation is gotten in almost the same way that of the planetary equation is gotten. Okay? You take this part, get the solution, and substitute on the right hand side. Okay? In what we call successive approximations. So the solution is of the form u is equal to u0 cos phi plus gm on c squared u0 into 2 minus cos squared phi. Okay, there are very good textbooks that elaborate the solution. You can go through them and see how the solution is gotten. Okay, so the solution is of this form. Okay, and mostly that solution is written as u equal to ax plus b into 2 minus x squared. So our a is u0, our x is cos phi. Okay, our b is all of this. So we can write that equation like that. And then again we can identify this equation as a Cartesian equation. Cartesian equation for a conic section. A conic section. Okay, it's a Cartesian equation of a conic section. Okay, and once you start bringing in conic sections, you know that there is curvature. Okay, once you start bringing in conic sections, you know that there's some sort of curvature. Okay, there's some sort of angular change, be it parabolic, be it hyperbolic, be it elliptical, be it circular. There is some sort of a change in angle. Okay, there's some sort of a change in angle. Are we together? The class is so quiet. Maybe we need to pee somebody to cry, like Prof was saying, so that we can cause some disturbance in the system. Okay. so that we can cause some disturbance in the system. Okay. It can cause some disturbance. I used to watch some videos on social media. Okay, where maybe at times you see somebody will be moving, somebody will look for an artificial snake. Okay, and then he will be moving around with it and frightening people on the streets. Yeah, something like that. So you are moving, you will just come and put it inside your back. Before you want to realize, you see a snake, you see somebody jumping. Okay, and actually those things are not good. You can kill somebody. Okay, you just look for a rubber snake and be moving around and playing pranks on people. Okay, you can do that and somebody can. Okay, somebody can just collapse. Okay. So it's not every prank. This is what we used to call April Fool. I don't know whether they are still doing it these days. They used to call it April Fool. Okay, somebody will just get up on the 1st of April and tell you one funny story. Okay, and then you take him serious. At the end of the day, you discover the story is not true. Okay. I remember when I was when I was still small, I went to our neighbor and I said my mother has said that she should give her 2,000 naira. That she will give it back later in the afternoon. So when she gave me the money, I said, April Fool. Okay. And the woman was looking at me, she could not collect the money back. She was just smiling. Okay. All right, so let's look at a photon that is grazing the edge of the sun. Let's assume this is the sun. Okay. And then we have a photon that is grazing the edge of the sun. It's approaching the edge of the sun. Okay. We have a photon like that. Let's call this point Q. Okay. And then the radius is R. The radius is capital R. Okay. So actually, it will come like that and take this path. A path similar to this. Okay. Not too good in drawing. So we have that. Okay. So at that point Q, our phi is pi over 2. At that point Q, our phi is pi over 2. So what will be our x from this equation? Remember, x is cos phi. Okay, we replace x by, so x is cos phi, so it will be cos pi over 2, which is what? Which is 0. Okay. So our u will be, so at this point our u is 1 over r. Our u is 1 over r. And if our u is, so these are like some initial conditions. If our u is 1 over r, then our b will be what? So this is 0, this is 1 over r, this is 0, so you have 2b here, and they have 1 over r here. So our b will be, what will be our b? Our b will be 1 over, is it 1 over 2r? Our b will be 1 over 2r. If this is 1 over r, this is 0, this is 0, so 2b equal to 1 over r. So b will be 1 over 2r. Okay? So as the photon is moving away from the sun, okay, r will turn to what? The photon is moving away from the sun. From the sun, our r will turn to infinity. Okay? It's moving away from the sun, then our r will increase to infinity. And if r is moving to infinity, our u will move to 0. And our phi will move to phi infinity. Okay? As our x moves to x infinity. So in that case, what happens? What happens to our equation? What we are now saying is that, so this is another boundary condition we want to apply. So at r is tending to infinity, u tends to 0, phi tends to that, and x tends to that. So we need to substitute them into our equation. So we are going to have 0 to be equal to a x of infinity plus b, okay, into 2 minus x of infinity squared. Okay. So we can use that to solve for x of infinity. Or x of infinity, remember this is a quadratic equation. It's a quadratic equation in x of infinity. Yeah. So we can solve for x of infinity, and if you do that, we'll get either a over b or x of infinity equal to minus 2b over a. You can get either that. So we can be able to get that. Okay. So with those values of x, we can be able to get our cos phi of infinity. Okay. And our cos of phi of infinity will be, we can choose any of them. Okay, we can choose any of them. Okay, but this one, let's work with this one first and see. So that will be minus 2b over a. And if you solve this equation, phi of infinity will just be pi over 2 plus 2b over a. So it will just be that. So in fact, you see, our phi here was pi over 2. Can you see that? Our phi here was pi over 2. That is at the surface of the sun. But as the photon is moving away towards infinity, it's no longer pi over 2. There is an additional term. So the light has been deflected by a small angle. The angle is no longer pi over 2. The angle has some sort of addition or subtraction from it. So there is some sort of deflection. Do you get the point? So the light is being deflected. So the rate of deflection is this 2b over a. Okay? So we can call that one delta 1, which is just the deflection there. Okay, it's a deflection, which is what we are interested in. Okay, and you can go further to show that that deflection is related to the mass of the body and the radius of that body. You are meditating. You are meditating. Okay. Okay, and that deflection for the sun is around 1.77 seconds. Okay, very, very small change. It's a very, very small deflection. Okay, so these are some of the gravitational phenomena we'll be looking at. How many of them? There are 6. Okay, there are 6 of them. Okay, so let me now introduce what we'll be trying to do. Any questions so far? Yes. Can Whether can we just take cos? Remember, for you to solve this, this must come to this side, equal to 0. Then you now take the, okay, when you now take the inverse, it gives you pi over 2 because cos 0 is, so it's something of that form. You can go back and see how you handle those how you handle those trig equations. Remember, I have something like, I have cos x infinity equal to minus 2b over a. Okay, so I have cos x infinity plus 2b over a equal to 0. So what would now be my cos that? So you try to solve this equation. Okay, but you are going to have some pi over 2 plus, because this will only be 0 if this is pi over 2 plus something. Okay, maybe multiples of pi over 2. That's what will give you 0 here. So it's something like that. Okay, so we've laid the foundation, and we now want to see how we can be able to apply the small knowledge we have gathered, okay, to solve problems that are physically relevant. Okay, so what I want us to look at is astrophysical study of gravitational fields around spherically symmetric plasma stars. So Prof has been saying a lot about plasma. Okay, he has been saying a lot about plasma. So we'll be working on gravitation. We'll be working on theoretical astrophysics, and we'll be using general relativity. Okay, so those are that's what we'll call, maybe we'll call it a thematic, area. At times when you want to submit a research paper, they'll ask you to choose the thematic area. Okay, maybe you pick theoretical physics, they will now give you sub-areas again. Which of them you pick it. Okay, and each of them has its own number. It has its own number. Okay. So how do we go about that? Okay, so we have the conventional star model that is used in general relativity. When you look at general relativity and you want to study stars, stars mostly in general relativity are considered to be gaseous spheres. Mostly. You see any problem they are solving, most textbooks, they will assume stars to be gaseous spheres. Okay? And most of the time we assume that the stars consist of hydrogen. Okay? And there is a thermonuclear reaction taking place and giving helium, blah, 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 and so on. Okay? And then it's also assumed that stars have inhomogeneous interiors. Okay? Inhomogeneous interiors, and that they are extremely hot, and there is a dense central region. Okay? Those are facts we have. Okay? Prof has said so much about corona, protosphere, and so on and so forth. So we have that. Okay? And as I said earlier, we also say that there is hydrogen. Okay? Much hydrogen producing energy in maybe nuclear fission reactions. Okay? And so this is the conventional star model that we have. But there are other star models that are not popular. Okay? There are other unpopular star models. There are star models which consider the interior of a star to be made up of different states of matter. Okay? And then there are other models which think that the energy from the star is not by nuclear reactions. That there are some non-nuclear stellar energy sources within the star. Okay, and many others. If you read on that, you will see so many star models. Okay. Around the 1920s, the first plasma star model was developed. Okay, which assumed that a star is much populated. It has a much populated interior. That the interior is not only made up of gases, but there are other materials inside that makes the inside to be more heavily populated. And actually there are astrophysical evidences to prove this. That the interior of stars is not only made up of gases. Okay? It's not only made up of gases. Okay, but when this model was developed, it was not convincing to the scientific world. And why was it not convincing? Because it had no sound mathematical framework. The mathematics that was used to develop it was not so strong. Okay? So there were a lot of arguments around it. Actually, the model was only formulated on arguments and observational facts. Okay, when you go to cosmology, you will see so many models that are built on arguments. Okay, just arguments. So many models. Just arguments and counter-arguments backed with some observational facts and so on. So with that, you can build a whole model. Okay, so this plasma model was built on arguments with some observational facts. But because it lacked a mathematical framework, a strong mathematical framework. Yesterday, Prof said that you cannot study physics without mathematics. So anything you bring and it has no mathematical framework, the physics world will look at it to be not convincing. Okay, it will not be convincing to the physicist if the mathematics is shaky. It's shaky. Okay, that's why at times I used to pity people who think they can study physics without mathematics. Okay, because today we have so many students who are shying away from mathematics. Who are shying away from mathematics. They want you to give them an area of physics where you will not see any equation. I'm yet to see that area of physics. I'm yet to see that area of physics where there is no where there is no equation. There is no equation. Okay, so, but the gas model that was there had a well-formulated mathematical background. Okay, with the mass luminosity relation. Okay, and though the gas model could not and cannot account for some things that are observed physically. Okay? But since he has a good mathematical background, it is considered that those things that cannot be resolved are just some difficulties that will be resolved in future. Okay? They are just some difficulties that will be resolved in future. Okay? So we also have what we call the Jeans plasma star theory, okay, where he looked at an ideal liquid. He looked at the equations of state from classical physics, and further deductions are not possible as it does not contain characteristics of stellar mass. So he actually tried to come out with a model for plasma stars, but the model is lacking because it doesn't have characteristics of stellar mass. Anything you are coming with as a physicist must have observational backing or experimental backing. If it doesn't have, it will be difficult to convince somebody. Okay? So around 2009, these two Russians, Borisova and Rabonsky. Okay, Borisova and Rabonsky. Actually, I worked with Rabonsky during my days of my PhD. Okay, we did a lot of, he actually assisted me a lot. So I worked with him. So I reviewed one of their books. That was translated from Russia to English. So I reviewed the book, and the thought of general relativity is the most accepted theory of gravitation. The thought of trying to look at this plasma star model using general relativity. So they actually developed a theory of plasma stars using general relativity in a book that is more than 700 pages. So they developed that theory. Okay? So they used general relativity to study plasma stars. Okay? And in that theory, they actually brought in the condensed matter within star interiors. Okay? So they considered the condensed matter within star interiors to build their theory. Okay, to build their theory. So what I want us to do is to use their theory in order to study symmetric plasma stars. Okay, to study symmetric plasma stars. So what are the questions we are going to ask ourselves? What are the questions we are going to ask ourselves? The first question we are going to ask ourselves is, how are Einstein's gravitational field equations, exteriors to stars, different from Schwarzschild's? Remember, when we started Schwarzschild's, I told you that Schwarzschild's is the solution to a spherically symmetric body. Okay, and the interior of that body is made up of gases. So when we now look at this other model where the interior is not made up of gases, how will the gravitational field equations be similar or be different to Schwarzschild's? Okay, so we are supposed to bring Schwarzschild's gravitational field equations, and then we get our own gravitational field equations from using their own model. Then we compare the two and see how is their own similar to our own. How is their own different from our own? So that is the first question. The first question we are going to try to attempt a solution to. Okay, the second question we are going to try to attempt a solution to is, are solutions of the field equations similar to existing fields? So we'll not only get the field equation, we'll also attempt solutions. That is involved. Okay? So we'll not only get the field equations, we'll also attempt solutions to the field equations. And then we'll get the solutions and try to see how are those solutions similar to other solutions. How are those solutions different with other solutions? Okay, so do you get a picture of what we are trying to do? Okay, then the third question is, what are the consequences of the state of matter to the motion of test particles and photons in this field? Prof said the other day that there's a fourth state of matter, and that fourth state of matter is what? Plasma. Okay, so we are now going to see whether studying the gravitational field around that, okay, whether it has some consequences on test particles and photons. Okay, but there is one aspect which we are not going to go into, which Prof asked me yesterday, whether we are going to consider magnetic effects. Okay, we are not going to consider magnetic effects to make life easy. Okay, to make life easy. Later on, we can try to see how to incorporate that. And that's why I'm very interested in Prof's lectures, because I'm trying to see how to bring in that. Okay, how to bring in magnetic effects. Okay, how to bring in magnetic effects and try to see what is happening. Okay, so there is what we call whether it's combined field theory, where all the forces are tried. We want to harmonize all the forces into one. Okay, so if you can bring in the effects of electromagnetism, okay, into a gravitational field, it gives you more better, there's even what we call electrograviton, okay, electrogravitational fields, where you are not trying to marry those two. Okay, so in this case, we will not go into that. But some of you who are interested in it, you can join my group, okay, so that we can extend this further. We can extend this further. We have done that in some few cases. Okay, but there is still much to be done. And then the fourth question we'll ask ourselves is, how unique are planetary equations and deflection of light in this field? Okay, how is it unique? And then what are the effects of the field on other gravitational phenomena? Okay, so these are some of the research questions we'll try to answer. Okay, So any questions so far? Any questions so far? Any questions so far? So we have about 3 or 4 or 5 objectives that we'll try to achieve during our stay here. Okay. So maybe I will introduce those objectives tomorrow. Or maybe later in the afternoon after we have eaten food. Then I can introduce some of them. Okay, so that we can start work on them. Okay? Because actually each of these research objectives can produce a paper for us. Each of them can produce a paper for us. Okay, so we'll try to do that. Okay. I also want to be part of that pot. That's why I've stopped, so that I can join you in. Okay. So what I'm saying is that maybe we'll start looking at the research objectives later. Then from there we will now group ourselves and try to see how to work. So every day will be progress report. Every day, each group will give us their progress report of how far they have gone. Okay, when you're having difficulties, I'll come in. So, ongoing, I will be sitting behind there. You wear this on you and talk. Okay, so I think this is a convenient point to stop. Yeah, that's what we'll do that later.